Hello, and welcome to the Data Engineering Podcast, the show about modern data management. Are you tired of data migrations that drag on for months or even years? What if I told you there's a way to cut that timeline by up to a factor of 6 while guaranteeing accuracy? Datafold's Migration Agent is the only AI-powered solution that doesn't just translate your code, it validates every single data point to ensure perfect parity between your old and new systems. Whether you're moving from Oracle to Snowflake, migrating stored procedures to dbt, or handling complex multi-system migrations, they deliver production-ready code with a guaranteed timeline and fixed price. Stop burning budget on endless consulting hours. Visit dataengineeringpodcast.com/datafold to book a demo and see how they turn months-long migration nightmares into week-long success stories. Your host is Tobias Macey, and today I'm interviewing Andy Warfield about S3 tables and S3 vectors and how they fit into your overall stack. So, Andy, can you start by introducing yourself?
Hi, I'm Andy. Nice to meet
And do you remember how you first got started working with data?
you. Holy smokes. That's a really long time ago, Tobias. I guess I've worked with computers and software forever. I went to grad school in the UK and I worked on operating systems and networks and security and hypervisors. And so I spent a lot of time really excited about like low-level bits of the stack, and in particular about like how we could make changes there that let us do cool new things with computing, like virtual machines. And I guess I've kind of spent like most of my career slowly moving up the stack, getting excited about like new problems. And so I went from the virtualization stuff to doing a lot of work at like block level storage virtualization, and then working on S3. And now I spend a lot of time at Amazon working with not just the S3 folks, but all of the storage teams, as well as some of the teams that consume the storage stack, like the analytics folks and the AI/ML teams.
And so, in terms of the S3 tables and S3 vectors functionality, I imagine that everyone who's listening to this has had at least some exposure to S3, given that it is largely the backbone of the internet at this point. But in terms of the tables and vector functionalities, they're a reasonable divergence from the original objective of S3 as being effectively a bag of bits where you could put things and have a good expectation that you'd be able to get them back out again. And I'm wondering if you can just start by giving an overview of what are the goals that you have in the introduction of the tables and vectors functionality.
Yeah, this is a question that's been on the team's mind a ton over certainly the past couple of years. I don't know that S3 set out to be a bag of bits. First of all, I occasionally go back and read the very original S3 PR FAQ, like the thing that the folks wrote when S3 first launched about what it intended to be. And even in that doc, they talk about managing all the world's data and about being a file system for the internet. And so I do kind of think that S3 has always sort of, really just aspired to make data as effortless to work with as possible. I think the thing that's been really interesting about that is over the first bunch of years that I worked on S3, I think we were still learning a lot about just scaling the object workload. And, we were growing like crazy. We were doing a ton of doubling down on making sure that like we deeply understood the data path and the durability path and stuff inside the system. We stepped into S3 Express because we were increasingly seeing folks move to more actively using S3 for things like analytics and ML training data and stuff like that. And then over the, I guess like I want to say like 2 or 3 year period leading up to the launch of S3 tables last December, we'd already seen loads and loads of analytics workloads, especially on top of Parquet. And the move to open table formats, and especially Apache Iceberg, was really steering us into a lot of customer conversations where folks were using S3 as like a table store for databases. And so I think the kind of like interesting, I guess, sort of like slow aha moment that the team had, I don't know that it was really a moment at all, but like I think slowly came around to the idea that S3 was not specifically objects, and it was more a storage system that had these great properties in terms of elasticity and durability and scalability, these things that the team kind of internally calls like the fundamentals, and that we should explore using other data types, because the fact that we didn't have support for more advanced data types was a source of friction that customers were having to build on top of.
And so, as you mentioned, S3 Tables was launched a few months ago. That has been out in the wild for long enough now for people to start investing heavily into it and build their own use cases around it. And since we didn't really define what these things are, I'll give the brief overview of S3 Tables is an Iceberg native storage medium for S3, as well as now a Iceberg REST interface as well for the catalog implementation. And S3 Vectors is a similar paradigm, but for vector storage, which has obviously become all the rage because of the recent hype around AI and semantic search and retrieval augmented generation, etc. And I'm wondering how the experience of building and launching S3 tables helped to inform the work that you've been doing with S3 vectors up to its launch.
That's a great question. So it is absolutely not true that we shipped tables and then like decided what to do next and shipped vectors. We shipped tables about 7 months ago, and vectors took a little bit more work than that. So we were working on the vectors project at the same time that we were working on tables. Tables was a thing where a lot of especially our largest analytics customers had grown reasonably sophisticated workloads on top of Parquet, and they wanted to be able to do like fancier things, like all of the stuff that Iceberg really provides, upserts, right? Being able to do appends into existing tables more cleanly, being able to manage performance for really large tables, change schemas, stuff like that. And so a lot of the launch there was Iceberg already existed and people were able to use Iceberg on top of S3. And the pull that we got into launching tables as a sort of managed table construct was that it wound up being a really common story from customers that Iceberg was a lot of work to run, right? That, they had to schedule compaction jobs. They had to think hard about performance and sort orders and stuff like that. In a few cases, having all of the Iceberg metadata and data files exposed in the same bucket meant that they, did their own work on compactors and got themselves into like mixed up references that meant that they couldn't access their data and stuff like that. And so we kept having this customer conversation where folks were like, I feel like suddenly I'm managing my storage system and isn't that your job? And so that was the thing that led us into tables. I think the way that Iceberg and tables were really influential on what we've done with vectors is with these higher level constructs, because they're all kind of built on top of objects under the covers. The table construct does appends and writes to the table as a sort of copy on write thing, right? Like Iceberg creates Git-like snapshots with updates. If you do lots of small writes, you get lots of commits into the table. And then there's a background compaction job that tears through and reads everything and writes it back out in a format that recovers deletions and also makes it a lot more efficient to do reads. If you look at the sort of like vector workload, it has a lot of the same properties. And so for vectors, internally, there's a similar kind of thing of being able to do efficient appends and then having an internal compaction task that does all of the vector indexing and puts the vectors into a format that's more efficient for querying.
One of the interesting things with vectors is that it is not as well defined as far as the workloads that people are building with vectors, because there's still a lot of flux in terms of how people are building with it, which vector implementations people are building on top of. There are vector storage where it's just give me a way to store n-dimensional arrays. There are vector indexes, which provide fast lookup and scans across that underlying storage. There are plugins to existing database engines, pgvector being the most notable. And then there are fully dedicated vector databases that are optimized top to bottom for vector storage, indexing, and retrieval. And obviously, S3 as a medium for storing vectors is not an end-to-end database, because it is also a more generalized system that has vectors as one of its capabilities. And I'm wondering how you're thinking about the role of S3 vectors in that overall context of the vector storage, indexing, discovery, and retrieval that people are building.
Well, this is another really good question about stuff. You're kind of like reading into a lot of interesting history. So one of the things I love about the S3 team, the entire time that I've worked on the team, is we have heated discussions about API. The team, especially folks that have been around for a long time, kind of know that like the API end of S3 is the one thing that we will live with for a really long time. And so there's a lot of effort to get that right, and a lot of back and forth on things. And with vectors, as you say, it's still kind of emerging, the shape that a vector API needs to take. And in particular, the thing that you mentioned about embedding models is absolutely true. And so, for folks that aren't as familiar, maybe it makes sense to take a step back on the vector thing. We have seen in S3 and Amazon storage generally, we work with customers with every imaginable type of data at every scale. And so it's really, really fun. It's like so exciting for me because I get to see all of these different use cases and understand, the challenges that folks have working with data. And vectors are a thing that, 5 years ago weren't really coming up in conversations, and that over that period of time, we've seen come up in all sorts of domains. The high level workflow around vectors, a vector is just literally like a mathematical vector. It's a multidimensional space. If you imagine like a two-dimensional vector, it's literally like an X and a Y. Those numbers are usually floating point numbers, although they're often low precision to save space. And what you do is you encode a piece of data and you place it inside that coordinate space, the vector space. And so if you imagine a two-dimensional vector space, like a graph that, like an XY plot that you could draw on a piece of paper, I could take a picture of a dog. I could pass it through what's called an embedding model, an ML model specifically designed to generate vectors. And that model would spit out some coordinates in that space, like 5.1, 4.2. And that location in the space would be where objects or images that were similar to that first dog image that I put in landed. And as I went and scanned in loads and loads of other images and generated embeddings and put them into the space, a good embedding model would place similar things close together inside the vector space. And so I could go, if I wanted to search for something, I could take a different dog picture and I could generate its vector. I could query for nearest neighbors of that vector, and I would get a bunch of other points that let me see other related pictures, hopefully of similar looking dogs. Now, none of the vector embedding models can really like embed enough information in 2 dimensions. And so it's very common for these models to have anywhere between about 500 and 2,000 dimensions, which is like kind of fascinating to me because I stopped being able to wrap my head around what a vector space looks like in about 4 dimensions, like really 3 and almost 4. And so the idea of these 1,500 dimensional vector spaces is kind of like a crazy thing to think about. But then you basically put stuff into that space. It clusters together with related things. The embeddings allow the model to basically assign semantics across a lot of different areas. And so, that dog picture might also have a pine tree in it, or it might be in front of my old house, or there might be like a fire hydrant. And if I went and generated an embedding for another picture that just had a fire hydrant, that dog picture might also show up because it's close in another aspect of the super high dimensional vector space. And so a thing that we kind of found with the design was the embedding models are undergoing a ton of research right now. And they're changing all the time. And new embedding models are emerging that are more and more awesome. As one example, there's a startup called 12 Labs that makes this really, really cool embedding model for video. They just launched their model on Amazon Bedrock. And with that video embedding model, you can take hundreds of hours of video and you can go punch in a query for something like a person doing push-ups. And the neat thing with some of these models is that they're multimodal. And so you can type in that question as text, and it will literally return you a set of offsets of scenes because it generates vectors for every scene that have that kind of content in them. And so it's one example of a vector index in search where you see folks in media like broadcasters being able to take a model like that, take thousands and thousands of hours of archival footage, generate scene level vectors, and quickly be able to, from a string search or a captured image, build highlight reels, right, or montages of related content in their archive. And so that's kind of one example. So when we designed the API, to get back to your question, we decided that the embeddings would probably have to be externalized. We didn't want to impose our choice on embedding model because we were seeing customers switch between embedding models, in some cases build their own embedding models. But we did decide that rather than strictly storing the vectors, that it was important to offer a query capability. right, to do approximate nearest neighbor query, because we were seeing virtually every customer that we talked to want to do that. They didn't want to like have to build their own index file format and scan through the vectors externally and do all of that stuff. And so we decided to do this cut line around storing, effectively any dimensionality of vector, indexing and doing queries on it, building that as an S3 construct. And the thinking is basically that this is a building block that really lights up vectors as a sort of connective tissue between all sorts of applications and arbitrary data sets. And so that's kind of where the API line is and what our thinking was behind building it.
Another nuance of the overall space in terms of vectors is the question of, to your point, there can be different levels of precision of the floats that are incorporated into those vectors, but then there's also the question of whether or not you support sparse or dense vectors, namely whether or not any of the dimensions or entries within those dimensions are allowed to be null or non-existent. And I'm wondering how you've tackled with some of those details of nuance around the types of embeddings that you want to support, particularly given the fact that it is a field that it is in motion and a constantly moving target.
Yeah, totally. I mean, I think what the team's done so far is so we first of all spent a bunch of time talking to existing like vector store builders, because a lot of them actually build on top of data that's in S3 because they're generating vectors on that data. And one thing that sort of we anticipated upfront with the design was that a lot of these existing vector stores have like really, really low latency, and they're designed for like a very high level of performance. And I think a bunch of that is on purpose, but also a bunch of that is a necessity out of the way that vectors are indexed and have been indexed in the past. Typically, to be able to navigate and find nearest neighbors in these like ultra high dimensional spaces, you use an index that is like a directed graph, and you kind of walk through this directed graph to find nearest neighbors. But a consequence of walking through that graph is you're round tripping to memory. Your walk may take, like many, many hops to get through the graph to find the appropriate neighbors. And running against S3, where the latencies to storage are potentially, like talking to hard disks, they're a lot higher than talking to DRAM on your local host. We couldn't use any of those types of indices. And so we kind of like got to a spot where we wanted to respond to the fact that we were seeing customers that built on top of some of the existing approaches to in-memory indices running into cost problems with really large data sets where they weren't sustainable over time, especially for vector stores that were only like, accessed for bursts of activity and then quiesced. And we wanted to give those things queryability and a cost basis that was much closer to something like S3 storage. But we also, out of the gates, wanted to still be able to serve those workloads that were like super, super performance demanding. And so we ended up talking to a lot of the existing vector stores. As an example, we spent a ton of time talking to the OpenSearch team inside AWS and kind of came to a position where we decided that we would build a thing that could hydrate into like a faster provision store and serve things at that level, and then quiesce down into S3 when it wasn't being used, as you needed to get down to that like storage level cost basis. And so from a workload perspective, supporting a lot of the embedding models that those existing stores were using kind of dictated a lot of our initial features, which are like really around vectors, vector queries, like straight up vector queries with a little bit of filtering, and the types of vectors that we see from the most common embedding models in customers, and the ability to like quiesce and get down to a lower cost, which we think really opens things up for broader use of vectors.
And then to your point of the various vector engines largely feeding off of content that resides in S3 as far as its origin, and then feeding it through these embedding models. Now that you have the ability to natively store and understand these vector types with S3 as the storage medium, how does that influence the ways that these other vector store systems are considering the ways that they interact with S3? And in particular, I know that, for instance, with streaming systems like Kafka, they usually have a means of being able to age out content to S3, so you have effectively infinite durability without having to keep all of that data resident on disk. And I'm wondering if you're seeing any of the similar patterns in these vector engines for being able to use S3 vectors as effectively an infinite buffer of data, but only keep some of it resident on disk for the hot path.
Yeah, totally. I don't have like I mean, the feature launched like 3 days ago. And so we don't have a ton of like super mature integrations at this point, but we've certainly been in a beta for the better part of a year with customers and some partners around it. That pattern that you're talking about of it's kind of like a CDC style pattern of aging out archival data has come up in a ton of conversations. It's interesting that for it's like one of the places that I was surprised to see vectors turn up. But like I've seen folks using vectors to spot similarities across time series data, and so even on the straight up streaming side, we're seeing like startups talking about integrations where they would keep the last whatever number of hours and then stage out, and they would maintain sort of like a active set of vectors for the stuff that they hold, and then destage those vectors out to S3 for more archival queries. See the same thing on OLTP style database integrations with tables wanting to maintain vector indices at the same time.
Another interesting element of this is in juxtaposition to S3 tables, where you had a concrete target in the shape of Iceberg, because Iceberg, as a specification and as an implementation, had a fairly mature ecosystem around it. There were lots of implementations and engines that used it, so you had a pretty good understanding of the types of patterns that you wanted to support. And in terms of the vector space, the only real analogous specification and implementation that I've seen as far as using vectors on storage, yes, is the Lance table format, which also has LanceDB as the query engine for that. And I'm wondering how you have been looking at the overall ecosystem, particularly with Lance as a reference, and thinking about the ways that you want the S3 vectors implementation to be a good citizen of the overall ecosystem without reinventing the wheel just for the fun of it.
We absolutely do not want to reinvent the wheel just for the fun of it. The Iceberg stuff has been a really interesting sort of like learning experience for us in that, as you say, we've had customers building on top of Parquet on S3 forever. Iceberg initially launched as a file format definition, right? There was no Iceberg API or anything like that at launch. And I think that the Iceberg community actually kind of found that in the original version of things, they were having to maintain storage specific library code for the things that they couldn't define in the file format. So Iceberg, to commit a new snapshot, needs an atomic swap operation on the root node, as an example. And so they had like 4 or 5 different backends for Iceberg that knew how to do that operation and like knew how to interact with like whatever storage type was behind Iceberg. And as that progressed, I think, as they wanted to move faster with certain features, and they wanted to be able to like integrate with lots of clients, I think that one learning there was that having to push a client software update to 100% of accessors to all of your like Spark clusters and things like that, whenever you made a change that impacted either how you interacted with the data on disk or the structure of the data on disk, was proving to be a real challenge. And on the Iceberg side, that gave sort of motivation to this Iceberg REST catalog API, which suddenly is like a REST API that allows you to talk about intention instead of directly integrating with the file format. And Iceberg right now is kind of this hybrid thing where there's the IRC, but there's also published specs for the manifests and the Parquet underneath it. And so it puts us in a neat spot with customers where customers love the property of Iceberg in terms of durability, of being able to see 100% of the files, right? They can potentially go through and walk the snapshots and just back those things up if they want to. They like knowing the structure of the format and being able to work with it. However, they also like the REST API end of things in terms of the ease that it brings to integration and being able to like move between versions and updates without having to like go and deploy a whole bunch of code. On the vector side, like you say, there was the Lance format. There's a couple of other, like, I think less mature formats for vectors, but there was nothing like Iceberg that fully cooked through, compaction, all of the ways that we wanted to take it. And in particular, we were pretty sure that the way that we were doing indexing would change as we learned, and especially as we got experience with customer workloads. And so we decided on that one, on vectors, to go in the path of starting with the REST API for things and kind of seeing where stuff takes us. And so that's where we are on it. I think if a format emerges that is like really, really universally adopted for representing vectors, I think we'd be like pretty excited about exploring doing something like what we did with Iceberg.
And then, as far as the technical implementation of S3 vectors, I'm wondering if you can talk to some of the ways that you've had to build layers on top of that substrate of the base S3 capability, and some of the ways that the overall S3 capabilities factor into some of the features that the S3 vectors functionality provides. And I'm thinking maybe in terms of the automatic lifecycle management, where you can either age out old vectors and delete them, or cycle them into the infrequent access mode or glacier and things like that.
You're like ruining all my future launches. The vector layer, if you want to think about the implementation, I'm trying to think about like how much detail it's useful to go into with you on this. So a lot of what is happening in terms of the actual data structure in there looks like a log structured merge tree, which is to say that updates arrive and we're trying to minimize the amount of IO that we have to do to be as efficient as possible on both the write path and on the read path. And so we want to work with young data to merge it and then get as little total number of objects underneath there to serve queries. And so the put API for vectors allows you to put a batch of up to 500 vectors. Those things accumulate and trigger a compaction task that folds them together. And then we do a whole bunch of math to calculate the clusters of vectors and the indices, and then quiesce them into like more like large, well-indexed structures. And we do a similar path on deletions for them. In terms of like the actual index structure and how the data is accessed, because it's S3 and we don't have ultra low latency access to the storage inside the system, and we really wanted to anchor on that cost basis, we tend to borrow ideas from some of the vector algorithms, index algorithms that have been published for that kind of storage, for higher latency storage. And the distinction in those algorithms is they tend to trade off achieving fewer round trips to storage with reading more data in parallel, which is actually a strength of S3. And so when you do a search, we kind of find the broad areas of the vector store where that data is, and we read all that stuff, and then we walk through it in memory to get the nearest neighbor results and return the nearest neighbors. And so that's kind of what's behind the query API. Now, I think this is a space where, as we understand, and a lot of why we launched as a preview was to really understand the usage and what the performance requirements were. And so I think that as we get a better understanding there, we're likely to make a bunch of changes to how all that's implemented to really like drive into especially the performance requirements of the workloads that we're seeing.
And then, as far as the index management, there are multiple implementations. HNSW, or hierarchical navigable small worlds, I know is one of the more popular ones. And I'm wondering how you're thinking about the functionality in S3 vectors as far as being able to evolve those implementations as new vector index styles emerge, or as new query patterns emerge, and some of the ways that the interface to S3 vectors needs to accommodate these changing patterns, the changing style and size and format of the vectors, etc.
The question you're asking is the thing that I think the design actually anchors on the most. The team intentionally chose APIs that anticipated the fact that we were probably not going to get the index right at launch. And I don't know what the count on the number of index redesigns that we've gone through since we started working on the thing is, but it's a few, right? We've like redesigned the index to reduce overreading and to reduce round trips to storage, and I think we're still learning there. And so a lot of what's attractive, and this is similar to what you see with Iceberg in terms of compaction, and even Iceberg in terms of version changes on the Iceberg spec, is it anticipates this idea to be able to go in and rewrite a lot of the underlying data during compaction and move forward without really impacting clients. And so the vectors implementation, because it doesn't expose the underlying file format, is even kind of better on that because it's completely described by a REST API. And so for the moment, I think that we will probably do lots of evolution in there, like I said, as we learn.
And then one of the other fun things about vectors is that in isolation, they can be useful, but you typically want to be able to reference them in conjunction with other information that you have, whether that is metadata that you want to link as attributes for being able to do filtering prior to doing an index scan on the vectors themselves. But I think more interestingly, epitomized by the PG vector use case, you want to be able to use the content in your structured data to be able to then also reference some of those vectors. You have S3 tables, you have S3 vectors, and I'm wondering how you're thinking about the potential for them to interoperate and be able to provide some linkages of data that resides in those two different features.
Totally. So, and this is absolutely where we are heading with this stuff. And so, first of all, a useful thing and a lot of what really like kicked off the vector stuff in the first place. But I feel like this is like, it was a point that surprised me. And I think it's like a really neat bit of intuition to grow about vectors and data is that number one, like I said, we're seeing like an enormous number of use cases for vectors. Obviously, doing retrieval augmented generation, the RAG pattern against like LLMs or other foundation models is a pattern where you use vectors as a bridge to let the model go and search a data set and find relevant data to answer a prompt. We also see vectors used in all sorts of other, like not even directly AI/ML applications, right? So there's really really interesting cases of vectors being used in medicine, especially in medical imaging, to quickly take an image, do embedding and search on it, and bring up a bunch of other cases that have images that have similarity to that image. So it's like a really fascinating diagnostic tool. We see it used in genomics to do a very similar thing where you've got like some kind of disease or set of like individual level properties, and you want to go and find similarities for that genome and see whether that property is expressed in other folks. And so we're seeing it used in drug development. We're seeing it used in like molecular similarity, also in drug development and stuff like that. The way that vectors are being applied, especially in science, is super cool. And it's fun to read about. It's been like a really exciting part of working through this stuff. When you think about data in S3, S3 has all of that data, right? We have a huge set of genomics customers. We have loads and loads of media and entertainment customers. We have customers in finance that want to use vectors for fraud detection and scoring and stuff. There's all these neat applications. What we did last year at reInvent was on top of tables, we launched this feature called S3 metadata. And what metadata does is it implements an S3 table on behalf of the customer's bucket that the service maintains. And so it's an Iceberg table. As you write data into the bucket, as you put objects in the bucket, S3 metadata comes through and you can configure it to produce either a journal of updates and deletions in the bucket or a table of the contents of the bucket. But because it's managed by the service, it has integrity. You can't go in and edit the contents of the table other than by modifying the objects that are in the bucket itself. And so by doing this, you get this like index that you can now issue SQL queries against to pick operations in the bucket. And that's a thing that we're excited about continuing to plumb into other operations inside S3. And I think that, one direction that we're obviously exploring is associating vector embeddings with that same metadata layer. And so really providing developers with the ability to like stitch together all of these different like views of their data into a single metadata store that you can then like integrate whatever tools you want against to be able to work with that data.
So, for people who are building with vectors, whether they have adopted one of these vector databases, they're doing something like a PG vector add on, how are you seeing from your early adopters the modification of any of the architectural or access patterns that they might have around vectors? And I'm wondering in particular, given the fact that the embeddings are typically something that you have to regenerate with some level of periodicity, either because you're adding new data or because you decided that you need to change your embedding model or change dimensionality, how they think about the role of S3 vectors as maybe an archival store of experimentation.
There was so much in what you just asked. So I'll call on my view on a few of the things you just said. One is I've definitely had the customer conversation that matches exactly what you said around like, I just have to regenerate embeddings every bunch of months because I'm like, in some cases, I have a team that's building an embedding model and, it's not good enough. And I'm just refining and refining and refining to get better results off of it. I've also talked to customers who have like a crazy amount of data, and running all of that data through an embedding model produces an enormous amount of new data and is quite a bit of effort and cost. On the intuition on the like vector side is for text data in particular, vectors almost express a sort of like information density on things. It's kind of neat. So when you do vectors on scenes in a movie or on images, like you're indexing something that's probably like hundreds of kilobytes to megabytes, and you're producing a vector that's like 4K. It's like it's an expensive index, but it's comparable to other indices that you might think about building. When you're indexing text, it's not uncommon to generate vectors at like a 300 token boundary or paragraphs or whatever. And now you're taking like literally like tens or hundreds of bytes and also generating something that's like potentially a 4K index entry. And so that ends up, it's one of the reasons that we saw customers want to not have to store all their vectors in SSD or DRAM all the time. But it's also something that kind of hints at the cost of generating the embeddings. And so we wanted to be able to like handle both of those cases and provide something that worked for them. But that's a reality of what we're seeing. The other thing that you said that I think is totally true is we see some customers that are working with reasonably mature pipelines where they have an ingestion path, they generate embeddings, and they're putting those embeddings into a large vector database, and they're doing search all the time. We have other customers that are doing a ton of experimentation. And a common path is, there's a pile of embedding models and data sets on Hugging Face. It's really fast to take that stuff. Last weekend, I was like doing load testing and usability, kind of like playing around with the final vector implementation. And I went on and grabbed a data set, the IMDb review data set. It's like 25,000 IMDb reviews, and used Sentence Transformer, which is an embedding model for Python that runs on the CPU on your laptop, generated embeddings for all those, put them into S3 vectors, and worked with that. And at the smaller end of the spectrum, like that, 25,000 vectors, we see a lot of desire to be able to do that and not need to stand up like a full instance of a vector DB to kind of like learn and experiment with vectors. And so I think like both ends of that are there. And I think we've tried to build a primitive that serves like both the early adopter tire kicking experimentation end, the more large scale end of things. And that kind of leaves a lot of the like really rich or super high performance vector functionality as a thing that we can like tier up into for customers that need that.
I'm imagining that this will evolve to a point where it is similar in terms of usage patterns to Iceberg, where you have Iceberg or S3 vectors as the bulk of your overall data because it's inexpensive to store and convenient to access. But then for things where you do want to have that low latency, high interactivity, you will either transfer that into a more dedicated engine or use some sort of dynamic caching capability. I'm thinking in particular as far as something like what StarRox offers for Iceberg, to be able to query Iceberg tables, but then be able to maintain a cache of them to improve the overall latencies. And then also to your point of reducing the barrier to experimentation or reducing the cost for low resource or low requirement use cases, can imagine S3 vectors as being a viable option for more of a serverless style pattern of, I just want to be able to throw something up and then people can access it however they want, but I don't want to have to deal with managing a fleet of servers to be able to manage their experience.
Tobias, that's pretty much exactly where the team's head is with all of these features. Is we want to make it as easy as possible to work with data, and like anywhere that we see friction on being able to build applications or like adopt tooling that works with data is a place where we really spend our energy. And like there's so many, a thing that's been like just so kind of awesome to see as validation of a bunch of that sort of doctrine on things is as we introduce these little features like conditionals into S3, or when we remove limits, or when we introduce these primitives like tables and vectors, we see it open up a bunch of use cases And like on tables, for example, I've had a ton of conversations with startups that are like, oh, this is actually super helpful for us because now we don't have to do the undifferentiated work of building this like scalable persistence backend. We can totally focus on, building a really, really high performance tier, or really building like differentiating domain specific, functionality around the data that ends up being ultimately stored down there. And so for all of this stuff, I'm really trying to work with the team, and we're really trying to build a sort of like best, base foundation for working with data that, exactly like you say, lets you turn on whatever tool you need and makes it really easy for folks to build those tools that bring like domain specific value to the data.
And as you have been building the S3 vectors and S3 tables functionality with your team, recognizing that vectors is still very early and likely hasn't seen a huge amount of broad adoption yet, what are some of the most interesting or innovative or unexpected ways that you have seen one or both of those capabilities applied?
On vectors, I mentioned a few, I think, with some of the like medical and finance applications. The vectors thing is, if you're interested, or your audience is interested in like just completely nerding out in an area of like computer science and information theory, go Google or use a chatbot or whatever to summarize like recent results in vectors. There are so many cool ways that these things are being used. It's actually quite surprising. One example that's really interesting in there is there's kind of a fun bit of work in visualization that can take these super high dimensional vectors and project it down onto 2 dimensions, which means that you can like view it inside a browser. And you get these like clusters, and there are some really cool like visualizations that allow you to take, like a pile of news articles, for example, generate embeddings, do a projection down into 2D and see like topics emerge inside there. And then in some of the visualization tools, you can click through into individual articles. And so there's stuff like that. There's similar examples where I've seen folks on the like data science side using vectors, and especially using like outlier detection inside the vector space. So like looking for the individual vectors that don't cluster well as things that represent poor data quality, right? Like they go through and go like, these outliers are either like broken results, or they're results where I don't have enough samples. And so even that kind of application is really, really interesting to see.
And as you have been building these features, working with the overall S3 platform and teams, what are some of the most interesting or unexpected or challenging lessons that you learned in the process of bringing these capabilities to production?
I don't know if I have any new lessons on this. It is a lot of work to ship software, especially with the expectations that S3 customers bring to something that is part of S3. And so, for all of these things, I always feel like we work like crazy to get a launch and a feature that is like just really, really simple. And getting to simplicity is a mountain of work. And this one's obviously still a preview, and it's still early, but the team's just doing like just a mountain of work on all of the aspects of running a S3 scale storage service that are or storage feature that are just needed to keep like all of our durability commitments and availability and everything else. And so I don't think that there's like a specific thing in there. It's all of the things that are required to get to the kind of operational posture that we expect for these.
And for people who are considering or evaluating an implementation of Iceberg cataloging and maintenance or vector storage and retrieval, what are the cases where either S3 tables or S3 vectors are the wrong choice?
Oh, that's a good question. Well, I mean, on the vector side, we kind of talked about it a bunch, right? On the vector side, I think if you need so I guess it's probably two things. If you need super duper low latency or very, very high transaction rates, query rates against the vector store, S3 vectors is probably not the thing for you. It's great for most workloads, I think, but I think for bursty workloads requiring really high performance, you're probably a lot better off to work with a dedicated provisioned in-memory store. Tables is a little bit more of a complicated answer in that Iceberg itself, I think, is still a little bit early. And so I think on tables, there's like a different answer between the sort of like analytics use cases and what the team wants S3 tables to be. And what I mean by that is Iceberg has existed for, I don't even know what, like 7 or 8 years at this point. It's been around for ages. It's really gained a ton of popularity in the last 3 or so years. It's well integrated into big open source analytics frameworks like Spark, but also, it's supported by things like Daft and all the various Iceberg accessors and other like sort of emerging runtimes. I think on that side of things, Iceberg is in pretty good shape. And if you're running a large Spark cluster or you're thinking about building a data lake, S3 Tables is a better Iceberg experience than running it on your own. It has better performance than running Iceberg on its own on S3, and I think it's in a really good spot. The place that we aspire to take S3 Tables is that it should be a programmatic table construct in the same way that objects are. And right now, the sort of like API surface for that, some of the workload surface, like loads and loads of really small updates from lots of clients, are things that Iceberg itself is not all the way there yet. It's like an area that the community is working to improve and that we're also working to improve. And so I think that there's probably a ways to go on S3 tables being like a first-class programmatic primitive as a table that you just use when you're building an application, but that's where we want to take it.
And as you continue to build and iterate on the S3 tables and vectors features, you've mentioned a few of the forward-looking capabilities that you're looking to implement. I'm wondering if there are any particular projects or problem areas that you're excited to explore.
There's loads. There's always so much more stuff to explore than we have time to look at. I think, I mean, Tobias, on this stuff, you start building these features, and it's so fun to steer S3 in these new directions. And you find yourself like refining and refining and refining to just get the absolute core of the thing out so that you can learn from folks and so that you're not like getting caught guessing wrong on shipping a bigger thing than folks can use. And then they get it. And then immediately, the customers that like try it and hopefully love it, call out all of the things that you have like not built. And usually the first tranche of all of those things are filling in the set of S3 features, which is like a pretty rich set of features. S3 is almost 20 years old, almost 19 years old, I guess, at this point. And so, it's filling in all of the stuff that you mentioned earlier, like lifecycle policy and cross-region replication and all of that stuff. And so I think for both tables and vectors, there's a ton of effort that the teams will fall into in terms of making it like a first-class, like rich primitive that supports all of the ways that people use objects. And at the same time, I suspect that we'll do a lot of feature-specific work, but that stuff will likely roll out a little bit more slowly, given the focus on just filling things out right now.
Are there any other aspects of the work that you've done on S3 tables and S3 vectors or the applications thereof and their overall position within the ecosystem that we didn't discuss yet that you'd like to cover before we close out the show?
We talked about a lot of stuff. No, I think that's about it. I'd love for folks to kick the tires on these, and I'd especially love to hear the stuff that we're getting wrong.
All right. Well, for anybody who wants to get in touch with you and follow along with the work that you're doing and give you some of that feedback you requested, I'll have you add your preferred contact information to the show notes. And as the final question, I'd like to get your perspective on what you see as being the biggest gap in the tooling or technology that's available for data management today.
Wow, that's a good parting one. I don't know, Tobias. I mean, I don't think it's a single thing. I think the reality is that that until we're at a point where you can just ask questions and where it is like, like 0 seconds to being able to get value out of your data, we're probably not done any of this stuff. And the reality is that we've come a long way, especially I think over the past like 5 years or so on being able to put folks in a spot where they can just get down to working with data and building. But there's still a bunch of work that we put onto developers that is outside of what they want to get done. And so I think, it's probably a bit of a dodge as an answer, but it's actually the way that I kind of think about the space.
The solution to every problem is another layer of abstraction. All right. Well, thank you very much for taking the time today to join me and share the work that you and the team have been doing on S3 tables and S3 vectors. It's definitely great to see those functionalities added to such a bedrock of the overall computing ecosystem. So I appreciate all of the time and energy that you and the rest of the team have put into that, and I hope you enjoy the rest of your day.
You too. Thanks for having me.
Thank you for listening, and don't forget to check out our other shows. Podcast.net covers the Python language, its community, and the innovative ways it is being used. And the AI Engineering Podcast is your guide to the fast-moving world of building AI systems. Visit the site to subscribe to the show, sign up for the mailing list, and read the show notes. And if you've learned something or tried out a project from the show, then tell us about it. Email hosts at dataengineeringpodcast.com with your story.
And to help other people find the show, please leave a review on Apple Podcasts and tell your friends and coworkers.